Good. So what are we working on today?
It's more like trig identities and solving trig equations.
Okay.
That kind of stuff.
All right. Let's start
Alright,
with
so
whatever you'd like to. Most people have quite a bit of trouble with verifying trig identities.
yeah, I'm having a lot of trouble with
Okay,
that.
let's do some.
Alright, so, or do you have something? Any in
Well,
mind?
I got plenty, but I'd rather do some that you have just because that's more appropriate for what you're taking. The degree of difficulty of the ones I give might not be the same. So
Alright,
if you have some, let's do yours.
okay, so the first one is cosine x, quantity, secant x plus, this is all in the parentheses, plus cosine x cosecant squared x equals cosecant squared x.
Okay? When they give you the method for verifying trig identities, the first thing they say is you always work with the more complicated side.
Yeah.
So we're going to attempt to prove that the left side is equal to cosecant squared x. Okay?
Yeah.
Now, the other thing they tell you is that if all else fails, turn everything into sines and cosines. Well, it's relatively, we already have a cosine there and a cosine there, and we can certainly use the reciprocal identity to turn that into cosine or sine, and the same with that, and the same with that. Okay?
Yeah.
So that's what I would choose to do here, is turn everything into sines or cosines. So before distributing, don't distribute until you have to. You may find you don't need to distribute. What's the reciprocal of secant?
1 over sine.
1 over cosine.
Oh, yeah.
Remember, there has to be a co in every reciprocal identity.
Yeah.
Now, let me say something else. Verifying trig identities does not have a real-world application. There's no way you're ever asked to do that in any real-world problem. The only reason that it's a part of every trig course is to get you to learn your identities. That's all its purpose is.
Yeah.
Okay, so let's review our identities. Most important one is the reciprocal. What's the reciprocal of tan?
Cotangent. 1 over cotangent.
What's the reciprocal of sine?
1 over cosecant.
And the reciprocal of cosine?
1 over secant.
Notice, every pair has precisely one co in it.
Yeah.
So there's no way you should ever put the cosecant with the cosine or the secant with the sine. Okay? Just a little memory trick, and it gets you to always get those right.
Yeah.
Okay? So this cosine here is already in sine or cosine, so we'll leave it there. How about cosecant squared? What's that equal to?
1 over sine squared.
Okay, now if I distribute at this point, This cosine times that cosine equals 1, plus cosine times cosine is cosine squared over sine squared. You with me?
Yeah.
What's cosine over sine?
Tangent.
So that's 1 plus tan squared. And what is 1 plus tan squared equal to?
What is it, cosecant?
Actually, it's secant squared.
Okay.
So, let's back up a step. Cosine over sine is not tan, it's cotan.
Cotangent. All right.
Okay? And 1 plus cotan squared is equal to cosecant squared. Let's review our trig identities. Most important one is this one. What's that equal to?
That one's equal to 1.
Okay. This one's a little different. Notice that it's tan squared plus 1 equals secant squared. You need to memorize that. You need to memorize that. The third one is just the cofunctions of the second one. Well, the cofunction of tan is cotan, and the cofunction of secant is cosecant. So you don't actually have to memorize the third one. Just remember the third one is the cofunctions of the second one. Now, when I say cofunctions, I mean cosine. In other words, you take the trig function and you put a co in front of it. So the cofunction of sine is cosine, the cofunction of tangent is cotangent, and the cofunction of secant is cosecant.
Yeah.
Okay? So these are cofunctions, which is different than reciprocals. Even though I use that memory technique on reciprocals, that there is one co in each pair, those are not cofunctions. All right, what else you got? You saw where we proved that one? Where it's, that's equal to cosecant squared, which was what?
Can you scroll up really quick so I can like get the full thing?
Yeah.
All right, thank you. And then so the next one is sine cubed. Yeah, sine cubed x times cosine squared x equals cosine squared x times sine s minus cosine to the fourth x times sine x.
Like that?
Yeah.
Okay. This one, we already have everything in sines and cosines. So this should be relatively simple. Which is the more complicated side?
The more complicated side is the right side.
So let's try to turn the right side into the left side. What's the first thing I see when I look at the right side?
Cosine.
What can I factor out of there?
Sine x.
What's the greatest common factor?
Oh, cosine squared times sine x.
Okay, what's left over?
Cosine squared.
Well, there's
Negative
a 1
cosine.
here.
1, and then negative
cosine, right?
Yeah.
In other words, if you put this back together again, you get this. This right here is a key thing to look for. What's that equal to?
That's equal to,
in other words, remember that you're rarely going to get it in the form that they ask you to remember it in.
Yeah.
So what is 1 minus cosine squared x equal to? Do the algebra on this. Subtract cosine squared from both sides.
So it's 1 minus 2
No, hold on.
times. It's cubed. It's sine cubed, not squared.
Hold on. In other words, there's your Pythagorean identity, right?
Yeah.
But the way you usually get it in a verifying trig problem is you usually get 1 minus cosine squared or 1 minus sine squared. So that's what you want to look for. That's equal to sine squared.
Yeah.
Okay, so if I substitute sine squared for that 1 minus cosine squared, I get cosine squared x sine x times cosine or sine squared x.
Okay.
Multiply that together, you get that.
Okay.
Okay? Now, I'm not sure to tell you what the secret is for these. I'm not sure there is a secret for doing verifying trig equations, other than knowing your 11 basic trig identities. There are 6 reciprocal identities you want to know very well. There are 3 Pythagorean identities you want to know very well. And there's 2 quotient identities. Quotient identities, what are these equal to? What's tangent?
Tangent is sine over cosine.
Which means cotangent is what?
Secant, or cosecant over secant.
Cosine over sine. Because remember,
yeah.
the cotangent is the reciprocal of tangent. So whatever the tangent is, the cotangent has to be the reciprocal. So when you're memorizing this is the only one you got to memorize.
Yeah.
So here's what you have to memorize. You have to memorize 3 reciprocal. That's it. You got to memorize 2 trig or Pythagorean identities, because you can always figure out the third one. And you got to remember 1 quotient, the tangent. That's it. If you can remember these 6 things, you can figure out the other 5 identities easily.
Yeah.
So 6 things, that's what you have to memorize. If you memorize these 6 things really well, you'll get really good at verifying trig identities. What else you got?
All right, the next one is tan x quantity sine x plus cotangent x times cosine x. Equals secant x.
That's it?
Yeah.
Okay. Notice that I don't always write the x.
Yeah.
Because when you're doing these, you might have to write 10 lines. So if I don't write the x, I save myself a whole bunch of trouble. And the x is superfluous, unless you have two variables. If you have an alpha and a beta, then you got to write them. But if it's all x or theta or something like that, you don't really need to write it.
Yeah.
Okay? So, again, that's in sine, that's in cosine, and I can easily turn that into sine cosine, that into sine cosine, and that into sine or cosine. So as long as that's the case, that's the approach I'm going to take. It isn't always the approach you should take. If you're looking at tangent squared plus 1, then that's a whole different story because that's secant squared, and you should go in that direction. But in this case, I'm just going to turn everything I can into sines and cosines. So get me started. What's tan of x?
Sine over cosine.
What's cotangent?
Cosine over sine.
So now we got, and we know that this is 1 over cosine. So that's what I'm looking to turn the left side into, is 1 over cosine.
So I think I'm a little bit ahead. So if you were to distribute the sine over cosine into the parentheses, it would be sine squared over cosine.
Okay.
And then it would be 1 plus 1. Like that.
Hold on. You just multiplied that by that. Now multiply sine over cosine times that. Sines cancel. One of the cosines cancel, and I'm stuck with just a cosine.
Yeah, so I was doing it like that's 1 and then cosine.
Okay, yeah. When you said 1, I wasn't sure. If 1 is a multiplier, you don't need to write it. If it's by itself, you need to write it, okay? So, now we have this. Okay, frequently you have to apply algebra. In other words, that's a big thing in verifying trig equations, is you need to be able to do your algebra. How do I add these two fractions? This and this.
Oh, alright, so that's the right is cosine over 1.
Well, hold on.
So then you do.
What's the common denominator? In other words, just like in algebra, in order to add fractions, we need to find the common denominator. What's the common denominator?
Cosine.
Okay. So if I turn this and put a cosine there, I got to put a cosine squared up there, right?
Yeah, well, in my class we call it the method. Like multiply.
That's fun.
So
yes, you're taking and multiplying top and bottom by cosine.
Yeah.
Okay. Now, what does this add to?
That adds to sine squared plus cosine squared over cosine squared.
Not over cosine squared, over just cosine. Remember that when you're adding fractions, the common denominator doesn't change.
Yeah.
So the common denominator stays cosine. What is sine squared plus cosine squared equal to?
1.
Okay, so this whole thing is 1 over cosine. That's what we were trying to make it equal. Now, if it bothers you that I manipulated the right side, then don't do that. In other words, turn this 1 over cosine into secant. And now it's exactly the way it started.
Yeah.
However, I will say that it's easier to do these if you do sometimes recognize that we're looking for 1 over cosine. In other words, if our strategy is going to be to turn everything here into sines and cosines, then I'm not going to end up with secant. I'm going to end up with 1 over cosine.
Yeah.
So it's a little easier to see if you know what you're headed for. I'm not trying to turn this into secant. I'm trying to turn it into 1 over cosine, which is secant. But in my head, I'm looking for 1 over cosine.
Yeah.
All right.
All right, the next one is cosecant squared minus cosine squared times cosecant squared equals 1.
Parentheses, like that?
Yeah.
Okay.
So
There's lots of things I could do here. I could turn this into sine and turn that into sine and go that route. But I notice that there's a cosecant squared there and a cosecant squared there. So,
and they subtract?
well, they factor. In other words, just like algebra, you're always looking to factor. If you can factor, that's usually the way to go. So factor that. What am I left with?
So cosecant squared on the outside, and then it's 1 minus cosine?
That's the magic thing to look for. 1 minus cosine, because there's 2 terms that I can turn into 1. What's the one term that I can turn this into? This is where you need the practice. You don't want to take more than about, if it's taking you more than 2 seconds to figure out what to turn that into, you need to review your identities. Because when you do these identities for a while, the first thing you think of when you see that is sine squared. Okay? So you're not going to be good at these until you make that association within 2 seconds. If it's taking you 10 seconds, you don't know your identities well enough.
Yeah.
Okay? Now, what is cosecant squared equal to relative to sine?
1 over sine
Okay,
squared.
so if I turn that into 1 over sine squared, what have I got? Sine squared over sine squared?
Cancel.
Well, it's 1. It's not cancel. Remember, we're trying to prove that it's equal to 1.
Yeah.
Okay. And we did it. Now, I could have taken a different approach here. Let's go back and I'll show you that there's multiple ways to do these things. I could have used my turn everything into sines and cosines. So I'm just going to do this. This is 1 over sine squared. Well, now notice that I've got a fraction with the same denominator and another fraction with the same denominator. So I can go ahead and subtract the numerators, leaving the denominator. And once again, recognize that that's sine squared. That's equal to 1. So there's all kinds of paths you can use to get to the answer. There's not one correct way to do it. I suppose one could say that the fewest steps possible is the correct way to do it, but not really. Remember what the purpose of this is. The purpose is to teach you your identities. Now, once you're really good at your identities, then you can start solving trig equations. And trig equations are very important in the real world. There's all kinds of real-world problems that involve solving trig equations, And in order to solve trig equations, you need to be very good at your trig identities. So they make up this game called verifying trig identities that everybody has to play, even though you'll never ever be called on in life to do any of these things. But you spend a couple hours doing trig identities, and trust me, your knowledge of your trig identities will be so much better. That's its purpose, just to get you better. If you want to be a good shortstop, we'd go out and have you practice fielding ground balls. Same thing here. What else?
All right. And now we have solving equations.
Okay. This is a little different, but it still calls upon you to know your trig identities.
Yeah.
What do you got?
All right. Q is 2 sine of theta minus 1 equals 0.
Okay. Treat this just like an algebra equation. What's the first step?
Add 1.
What's the second step?
Divide by 2.
What's the third step?
Factor x is sine.
No. In other words, if the sine of theta equals 1/2, then theta is equal to the inverse sine of 1/2.
So
These two statements right there are if and only if. This is by definition. If you know that the sine or any trig function of an angle is equal to a number, then that angle is equal to the inverse trig function of that number. Remember, you always take trig functions of angles and you get ratios. You always take inverse trig functions of ratios in order to get the angle. So you can look at this a couple of ways. What's the inverse sine of 1/2? You could look that up on your calculator. But that's one you should know.
Yeah, it's 30.
Yeah. So theta equals 30 degrees.
Or pi over 6.
Well, did they express a domain restriction on this equation? Usually when they give you trig equations, they say that theta has to be between 0 and 2 pi.
Yeah, that's what it says.
Okay, so that's not our only answer. There is another quadrant where the sine of that angle is equal to 1/2. What is it?
150 degrees.
Yeah.
Or
that's it.
5 pi.
That's right. I can write this as pi over 6 if you like, and this is 5 pi over 6.
Yeah.
All right, what else you got?
Cosine squared theta plus sine theta plus 1 equals 0.
Like that?
Yeah.
Okay. This is a little tricky. If you're trying to solve trig equations, you want to get everything in the same trig function. In other words, I've got a mixture of cosine and sine here. I'd much rather have it be all cosine or all sine. Which one is the easiest to convert to the other?
Sine to cosine?
Not really. Sine is equal to the square root of 1 minus cosine. That's not a particular easy conversion. However, cosine squared is easily converted to sine squared. Remember your primary, that plus that equals 1. So what's cosine equal to?
Cosine is equal to 1 minus sine squared.
That's the most important trig identity that you can remember. Not even sine plus cosine squared equals 1, but this. Because this is what they're always going to show it. You're rarely going to see sine squared plus cosine squared. It's too easy. They're going to make it one level more difficult. So they force you to convert this to this. Well, now notice that we have everything in sine, and in fact, we are looking at a quadratic. If I simplify this, then I turn this positive, and tell me if you don't understand one of these steps. You with me?
Yeah.
That's a quadratic. It's called a quadratic in sine theta. It's no different than x squared minus x minus 2. If I gave you x squared minus x minus 2, you would factor it into x minus 2 times x plus 1 and solve it, right?
Yeah.
Well, this factors also. Because it's a quadratic, it factors into sine theta there, sine theta there, just like x and x. This tells me the signs have to be opposite. And I need factors of 2 that subtract to 1. And the bigger factor needs to go with the sign of the middle term. Okay? With me?
Yeah.
Keep going. What are my two solutions?
Plus 1, or minus 1 and plus 2.
Okay. Can that be true?
No.
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 No. If I graph the sine curve, it never goes above 1 or below minus 1. So it's impossible for the sine of an angle to be equal to 2. So this is an extraneous solution. We cross it out, and the only solution we have is sine theta equals negative 1. Let's look at that curve one more time. Where does sine theta equal negative 1?
I don't know, it's 3 pi over 2 in...
That's your answer.
Yeah, that's it.
That's your answer. 3 pi over 2 or 270 degrees. And there's only one answer. Now, most of the time when you're looking at the domain 0 to 2 pi and you solve these equations, you always get two answers. In other words, if I'm looking to where sine is equal to 1/2, well, it's equal to 1/2 right there, but it's also equal to 1/2 there. So I would have two answers. But when it's 1 or minus 1, there's only one place in the unit circle where it's plus 1, and there's only one place where it's minus 1. Notice that there are 3 places where it's 0. It's 0 there, it's 0 there, and it's 0 there. So depending on what you get, normally you'll have two answers, but sometimes it's only one answer, like this one.
Yeah.
Okay, what else? When you're solving trig equations, think solving algebra equations, because that's the way you solve every one of them.
Yeah.
Okay, go ahead. I mean, that's the way you solve it until you get to the final step. And then you have to convert it to, well, what angle does that function equal that number? But up until that point, it's always just solving an algebra equation.
Okay. Next one is 2 sine x plus 1 equals 0.
Okay, this is very similar to the first one we did, only it gives you that. So what angle is the sine equal to minus 1/2? Now, I don't know how you do these, but the way I do these is I figure out what the first quadrant answer would be, and then I figure out which quadrants we're in and figure out the equivalent angles. So if this was a first quadrant question, what would x be?
30.
All right, so let's put that in parentheses. That's not our answer, because obviously the sine of 30 would be equal to plus 1/2. Which quadrants do we need to be in for the sine to be negative?
The third and fourth quadrant.
What is the third quadrant angle that's equal to 30 degrees?
210.
What's the fourth quadrant angle that's equal to 30 degrees?
330.
That's the way I do every one of them.
Yeah.
It's pretty straightforward this way. And of course you can convert this to 7 pi over 6 or 11 pi over 6. Okay?
Okay. Alright, solve each equation by using a graphing calculator for 0 greater than or equal to, or less than or equal to x less than 2 pi. Find x to the nearest individual radian.
I didn't hardly hear anything you said other than using a graphing calculator, which I happen to have now. I have a TI-84, a virtual one that I can bring up. What's the problem again?
It's 5 secant squared plus tangent x minus 9 equals 0.
Okay. Again, I've got two different trig functions here. Can I change them to the same trig function? That's my first thought.
Yeah.
Which one should I change it to, tan or secant?
Tangent.
Correct. What is secant squared equal to in terms of tangent?
Okay, so
tan squared plus 1.
Yeah.
Now notice what I've got. I've got a quadratic in tan x. Distribute everything. Combine everything. Well, the only thing I need to combine are the two numbers, and that becomes minus 4. Now, do you see why that's a quadratic in tan x?
Yeah.
What? No?
No, I do. I see
Okay,
it.
good. In other words, if you don't see it, then let's use a u substitution. I'm going to let u equal tan x. So this quadratic becomes 5u squared plus u minus 4 equals 0. And now you have just a simple polynomial to factor.
Yeah.
You can do that if you need to. But after you do it a few times, there's no point in taking that extra step. So let's just factor this. What's got to go here and here?
5 tangent and tangent of x.
What are the signs?
They're plus and minus.
They're opposite. So, but in this case, plus minus is not the same as minus plus, so I have to allow for both conditions. That's the way I do it. Factors of 4. Well, normally I would do 2 and 2, but I can see that 2 and 2 isn't going to work here. What does work? And you can do these randomly. I mean, there's not that many factors of 4, and there's not that many places to put them. So this is the phase of factoring that I call trial and error. In other words, I only have this many choices. I can do 4 and 1. I can do 1 and 4. I can do 4 and 1. I can do 1 and 4. Or I can do 2 and 2, 2 and 2. That's it.
Yeah.
So which of those 2 and 2 you can kind of tell isn't going to work. Because whatever 2 goes over there is going to multiply the 5, and I'm going to have a 10 tan, and there's no way I'm going to get it to that term right there. Remember that we're searching for that middle term to be plus tan x.
Hmm.
I'll give you a hint. The factors of 4 we want to use are 4 and 1. So which side's the 4 go on, and which side's the 1 go on, and which sign does it go with?
Okay. So it's going to be 5. Is it going to be 5 tangent minus 4?
Good.
And then tangent plus 1?
Yeah. Now, the reason I know that's right, and this is a key step, is I know the first term is right? I don't even need to check that. I know this term is right. I don't need to check that. What I'm particularly interested in whether I got right is the middle term. And the middle term you always get by multiplying the 2 inside terms and the 2 outside terms. Well, the 2 inside terms give you minus 4 tan. The outside terms gives you 5 tan. Add those together, you get plus 1 tan. That's our middle term. We did it right.
Yeah.
Okay, so we've factored it properly. Now, so that means what? What's the next step
That means
for solving for x?
you need to, well, it's going to be, we need to make each side equal to 0.
Set each of these products equal to 0. Because if you're multiplying 2 things together and it's equal to 0, one of them has to be 0. That's the only way it works. So we solve this by setting them both equal to 0. Okay, so 5 tan x equals 4, which means tan x equals 4/5, which means x equals what?
4.
inverse tan of 4/5.
Yeah.
Okay. The other one is tan x equals -1. Let's do this one first because we can do that without a calculator. No, yeah, we need a calculator to do this one. But where is the tan x equal to -1? What first quadrant angle is the tan x equal to 1?
Yeah.
Okay. Which quadrant are we going to be in that we are negative?
The second or fourth?
Okay. What's the second quadrant angle?
Second quadrant angle is...
That's the equivalent to a 45-degree angle.
135.
And the fourth?
315.
And I'll let you... That's 7 pi over 4, and this is 3 pi over 4 in terms of radians. Okay, so there's two answers. Now let's find two more, because where is the tangent equal to 4/5? Well, we don't know without a calculator. That's one of those ratios that's not a common ratio. So you need to go into your calculator. Here, I'll pull mine up and show you my new little toy here. This is pretty cool. I got this for free online. I just found it somewhere. And we want the inverse tan, so it's the second key, the tan key, 0.8. I don't even need that second parentheses. So 38.66 degrees is one answer. What other quadrant is tan positive in?
Third.
So what's the equivalent third quadrant angle to 38.66?
It's going to be 180 plus 38, so 180.
So here's our answers. 135, 315, 38.66, and 218.66. Now, what that means, if you were to go back into your original formula and plug in any of those four angles, that equation is solid.
Yeah.
Now, why do we have four answers? Well, every quadratic, you kind of expect two answers. And every trig function, if your domain is the unit circle, you expect two answers for every answer. You know what I'm saying?
Yeah.
In other words, this one produced two different answers, and this one produced two different answers. And that's what you expect. Sometimes if it's sine or cosine and it's a quadrangle, you're only going to get one answer, but usually you get two different quadrants.
Yeah.
What else? Got about 10 minutes.
Well, I only have one more question left.
Okay.
So, 12 cosine squared theta minus cosine theta plus 1 equals 0.
Notice that this is a quadratic.
Mm-hmm.
It's a quadratic because we have a term that is not being squared and we have a term that's being squared. There's lots of quadratics that are different than what you're used to. In other words, this would be the typical quadratic here. Okay? But there's other things that are quadratics that you might not recognize are quadratics. That is a quadratic. It's called a quadratic in e to the x. Why is it a quadratic? Because this term is the square of that term. And that's all you need for something to be a quadratic. As long as one of the variables is the square of the other one, then it's a quadratic. Even if I had something like this. X minus square root of x minus 2 equals 0. That's a quadratic. Doesn't look like one, but it is. It's a quadratic in square root of x. Because this term is the square of that term.
Yeah.
Okay, so now we need to factor this quadratic. Now, let me just tell you, because we're going to run out of time here, if you find a trig function that's a quadratic and you can't factor it, use the quadratic formula, and that will work.
Yeah.
Okay? I don't think we need the quadratic formula here because this factors in the 4 and 3. Oh, we do need the quadratic. Yeah, there's no way that we're ever going to get 12 in the middle. Is there? Even if I use 12 and 1, that gives me 13 in the middle. All right, this is a perfect example to end on. We can't factor it, we got to use the quadratic. So, it's not theta that's equal to minus b plus or minus square root of b squared minus 4ac. This is a quadratic in cosine theta. So it's cosine theta that's equal to all of that. Okay, so cosine theta equals, what's minus b?
Negative 1, or 1.
1. B is negative 1. So minus b is positive 1.
Yeah.
Plus
or
minus 1 minus 4ac. Well, that's 48. We have a big problem.
Okay.
What's our problem?
We have a negative square root.
Yeah, which means the answers are imaginary. We don't even know how to handle that with trig.
Yeah.
Okay, so not sure why they would give you this problem as your first problem. One that has no real solution. In other words, there is no solution here. Because our quadratic gave us an imaginary number. And we haven't learned how to handle imaginary numbers with trig yet.
Yeah.
All right. However, it's too bad they did that, because it would have been better if they would have given you one that actually had a real solution. Because, let's say we go to solve it, and we get, okay, cosine of theta equals minus 0.5 or 0.7. In other words, a typical quadratic formula solution would give you two answers that are real, right?
Yeah.
Well, now we apply the same thing. Where is cosine of theta equal to negative 1/2, 120 degrees, and 240. And where is it equal to 0.7? We'd put that in the calculator, come up with an answer and 2 quadrants for that. So it's very easy to use the quadratic formula to solve these, but you got to have real solutions, not imaginary ones. And they gave us an imaginary one here, unless I made a mistake. Would have been a lot easier if this was -1. You sure that wasn't -1?
No, it says +1.
Notice that if it was -1, now that is a positive number. That's 1 minus a minus, so that'd be 49, and I would actually have real solutions, both of which are not, I don't need it. If it's -1, then this factors into 4 cosine theta minus 1 times 3 cosine theta plus 1. Or vice versa, excuse me. Right?
Yeah.
So now my solutions would be cosine theta equals minus 1/4. You need to find the 2 quadrants where that's true. Or cosine theta equals 1/3, and there would be 2 quadrants where that's true and 2 different angles, and you would have 4 solutions, just like you would expect from a quadratic in the unit circle.
Yeah. All right. Cool.
All right. Any last questions, Lucas?
I did take some notes of the stuff that you told me I should have memorized, so I think I'll be pretty good.
Okay. There's definitely stuff in Trig that you absolutely must memorize.
Yeah.
And the sooner you do it, the better off you're going to be. And one thing is that page that has the unit circle on it, and probably the other thing are the 11 main identities. There are 6 reciprocal, 3 Pythagorean, and 2 quotient.
Yeah.
Make sure you got all 11 of those memorized. You got those memorized and the unit circle memorized, and you're in good shape with Trig. You really are.
All right.
Lucas, have a good week. I'll talk to you next Wednesday.
All right.
Bye-bye.